Hello everyone, my name is Shaktil Rahman, a student at the University of Toronto, and today I'll be talking about our paper. Most robotics pipelines consist of a modular sense plan act paradigm, where each module runs unaware of the others. This can cause problems, especially for visual localization systems, where a planned trajectory can lead to a region devoid of features, leading to poor localization quality. This in turn can cause poor controller performance or even instability. One paradigm to unify these three modules is that of belief space planning, which is the subject of our paper. The general idea behind belief space planning is found in the space of probability distributions, or beliefs. In robotics, where our state, action, and observation spaces are continuous, we represent our beliefs as Gaussians, parameterized by the mean and the covariance. The VecH operator here simply stacks the elements of the covariance matrix without duplicating symmetric terms. By maintaining and planning over a belief, we can account for the effect of motion and measurement uncertainty, and also allow for confidence-based collision avoidance. However, these methods are well known to suffer from the curse of dimensionality and history due to the large augmented belief vector and needing to keep around measurements throughout the trajectory. We tackle this problem of planning under uncertainty by formulating it as a stochastic optimal control problem. We assume that our underlying system is described with the following state dynamics and measurement model, corrupted by Gaussian noise. The task is then to compute a policy that minimizes the following cost function. However, optimal control formulations require both a cost and dynamics, which in our case are belief dynamics. Belief dynamics govern how a belief is propagated through time, given the current belief and input. In this work, we combine the prediction and correction steps of the extended common filter to describe how a belief evolves through time. Notice here that the dynamics are stochastic due to noise in the state estimate, motion, and measurement. Now we have a fully defined optimal control problem in belief space. We choose to solve this problem via differential dynamic programming, more specifically through the fixed horizon iterative linear quadratic Gaussian, or ILQG control. Details of how this controller works is described in the paper, but the main idea is to solve an optimal control problem over a horizon by solving a sequence of optimizations over a single time step, by starting at the end and working backwards in time. The benefit of this method is that the complexity increases linear with respect to the horizon length, which is especially useful for optimizing over longer trajectories in motion planning. However, ILQG requires smooth costs and dynamics, which is a problem in our case because cameras cause belief dynamics to become discontinuous. This can be seen in this toy example. Here, due to the input, the robot moves to a position where the feature is in the view of the camera. As a result, a measurement is obtained and the covariance, shown by this red ellipse here, shrinks. However, let's perturb this situation, where now the belief that the robot moves slightly to the right in our previous scenario, and now the feature is no longer within the field of view of the camera. Thus, no measurement is received and the covariance blows up. This drastic change in the belief due to small changes in input caused our belief dynamics for vision-based robots to become discontinuous. We thus proposed a novel, smooth probabilistic visibility model which works as follows. We assume that all features within a certain distance are visible, irrespective of orientation. We then scale the measurement information matrices, or the inverse noise covariance matrix, of each feature measurement by the probability of that feature being visible. To see how this affects our belief dynamics, remember that the posterior covariance is given by the covariance update equation of the common filter. If a measurement has a low probability of being visible, that measurement will not contribute to the posterior covariance. This can be shown to be equivalent to an expectation maximization method, and the details are shown in the paper. We propose the following for our visibility distribution. Define theta as the angle between the camera z-axis, or the optical axis, and the feature in question. The visibility distribution is thus given by the following equation, which when plotted out looks like this. Notice how the probability is 1 when theta is small, which corresponds to looking directly at the feature, and this probability smoothly trails off to 0 as the feature is closer and closer to the edge of the camera field of view. This smoothing allows for our belief dynamics to remain continuous and facilitates gradient-based optimization. Although the belief space ILQG method presented thus far works, there are still some problems. Notably, the method cannot handle hard constraints and thus requires tedious tuning of uncertainty costs, such as given here by the trace or determinant, against costs on the mean. Furthermore, there are no guarantees on localization quality. To this end, we develop a novel uncertainty constraint variant of belief space ILQG. In addition to the previous formulation, we now have uncertainty constraints, which look like the following. The A matrix here picks out the covariance elements of the belief, and we wish to have these values be below some predetermined maximum uncertainty values. We developed an augmented Lagrangian method adapted to ILQG to deal with these uncertainty constraints. The main idea is to transform the constraint problem shown previously into a series of unconstrained problems by replacing the cost function and constraint by the augmented Lagrangian. The augmented Lagrangian function is similar to the cost function of the constraint problem, but now has this extra penalty function, which is a function of some Lagrange multipliers of the original constraint problem, some penalty parameters, and the degree of constraint violation. Although many types of penalty functions exist, we use the following penalty function, which is a smooth approximation of the popular Powell-Hesteen-Rockefeller penalty function. This is an approximation of a quadratic penalty function adapted for inequality constraints. The main algorithm sketch is as follows. We initialize the penalty parameters, Lagrange multipliers, and some threshold parameters. We hold the penalty parameters and Lagrange multipliers fixed and solve the resulting unconstrained optimal control problem via the method we've already described before. Notice now that the penalty function is fully determined because the parameters here are fixed. Once we obtain a solution to this problem, we check if the constraints have decreased in value, where we use the threshold parameter here. If so, we hold the penalty parameters fixed and reduce the threshold. We then update the Lagrange multipliers according to the KKT conditions and resolve this problem. If the constraints have not reduced sufficiently, we increase the penalty parameters according to a fixed schedule, and then we resolve the problem. If the constraints are satisfied, then we terminate the problem. Otherwise, we go back to step 2 and reiterate. The way this method works is to drive an initially infeasible solution towards feasibility. We validate our method through simulation results. We use two robot models, first being a holonomic robot, and the second being a non-holonomic car-like robot. Both robots are equipped with a stereo camera, but in the non-holonomic case, we say that the stereo camera is on a pan-tilt mechanism where we can directly control pan and tilt rates. The environment is assumed to be known, so the feature locations and obstacle locations are known beforehand. To test our augmented Lagrangian ILQG method, we present the following scenario. We use the following cost function, which has a terminal cost that penalizes deviation from the goal state on the mean, and stage costs on inputs and avoiding obstacles. The constraints are as follows. We try 3 different variants of the constraints and see what effect they have on our method. We dub these loose, medium, and tight constraints, and there are 3 sigma bounds constraints on the x, y, and theta positions of the robots. The top left figure shows our 3D environment and 2 of the initial trajectories that we optimized. We show the results of our method for each level of constraint for the first trajectory. Notice how the optimized viewpoints change due to enforcing each level of constraint. At the loosest level, there is very little change in viewpoint, and this results in a lower final cost due to the smaller inputs. With tighter constraints, the optimized viewpoints change to focus on different features, which result in smaller uncertainty values, but at the cost of higher trajectory costs. These are completely natural behaviors that arise from our method, reacting to trying to enforce different levels of constraints with no tuning involved. This video shows how the constraint optimization progresses. In between outer iterations, the penalty functions are updated to continually drive the solution towards feasibility. To show the utility of using uncertainty constraints instead of soft uncertainty cost, we propose the following scenario. Say our application requires a maximum safe level of localization uncertainty, given as follows. We compare both our constrained method and the unconstrained soft method. In the unconstrained case, we have an added cost for penalizing uncertainty, which in this case is a trace. We compare our method against 4 differently weighted versions of the unconstrained method with varying costs and uncertainty. We test across both the holonomic and non-holonomic rho plots for both of the previously shown initial trajectories. We can clearly see that there is no consistency for the unconstrained methods as we change robot types or initial trajectories. What works for one has drastically different results for the others. However, our method satisfies the constraints in each case while also reporting lower trajectory cost. This is because our method dynamically adapts the penalties to constraint violations for each individual time step, with no manual tuning involved. Finally, we show that without our visibility model, the optimization fails to proceed past a couple of iterations and merely locks onto the nearest feature. Whereas with our visibility model, the optimization proceeds smoothly, and there's a greater change in viewpoint to focus on the features that are more important, resulting in lower final uncertainties. Thank you for watching.